Today's video is on collision theory.
So how does a chemical reaction really work? First of all, a chemical reaction is not an equation on a page or a simple matter between simple 2D objects. We need to look at the actual particles and their interactions. So here's my big question. What's actually happening when a chemical reaction takes place? Remember, it's a physical interaction between 3D particles. Those particles have mass, volume, velocity, energy, momentum, orientation, configuration, and so on. They're real things. Remember also they attract at a distance and repel when squeezed together because of those electron clouds. Also, breaking bonds requires energy, and forming bonds releases energy. The balance of these energies in and out gives you the delta H for a system. That configuration we were talking about is shape, polarity, and so on. So what actually happens when particles react? What's the real truth? Well, a successful reaction requires a collision. The particles need to be in the same place, at the same time, and need to be the right particles. They have to meet. But not every collision is successful. Which ones are? Well, the collisions that have sufficient energy to overcome the mutual repulsions and favorable geometry so the right parts of the molecules collide. That's the whole premise of collision theory. Right place, right time, sufficient energy, and favorable geometry. Let's see.
Okay, so here you go. Look. Here's the idea. Successful collisions happen when real particles interact in real space, and not every collision succeeds. So if these are the two particles, first of all, if this one's here and this one doesn't actually collide with it and goes by over there, that's not a collision. And if this one's here later and that one's there, that's not a collision. They've got to both be at the same place at the hinge. That's the idea of meeting, okay? So they've actually got to both arrive there. So say the particles arrive here and they are going to collide, but maybe they don't have a lot of energy. And their mutually repulsive electron shells cause them to deflect. So this one's going by, that one's going by, and they deflect, kind of bounce off each other. A glancing blow like this. Are you with me? And this one flies away there and that one this way. Or maybe they're aligned perfectly with one another, but they don't have enough energy, and so and then they fly back away this way. Make sense? So the electron shells are repelling one another. If you get very lucky and the electron shells can be overcome by the kinetic energy, and this one actually collides with that one with sufficient energy that they get past their mutual repulsions and actually hit each other, so they actually come in here in full collision. Still, these ones flew apart, nothing happened. Try it again. So here's another collision with enough energy, and they flew apart. Still no reaction. And there's another one with no reaction. And there's another one with no reaction. However, if you get very lucky, not only will you have enough energy and be at the same place at the same time, the orientation's got to be right. This molecule, in order to react with that molecule, I have to make this thing called an activated complex. It's a supermolecule. So if this one here and this one here actually come flying together, and it just so happens that they squeeze past their mutual electron repulsions and there's good geometry, they can make this thing called an activated complex. Okay? A supermolecule. Lasts for a very short time. It has very high potential energy, because if you were to release that, it would fly away again, right? Due to those electron clouds. So this thing here exists just for a short time, long enough for new bonds to be formed, old ones to be broken, and then the mutual repulsive electron clouds will throw these guys away. That was a single replacement reaction. Do you see that?
Yes.
Okay, so the idea is this. If they don't meet, no reaction. If they don't meet with sufficient energy to get past the mutual repulsions, no reaction. And if they don't meet with sufficient energy and good geometry, so that new bonds can be made and old bonds can be broken, again, no reaction. Collision theory gets us this as an absolute necessity for the reaction to occur.
So if this is how reactions occur, how can we make them go faster? Well, heating helps, which gives you more collisions and each collision having more energy. That's the big effect. You can break them into small pieces to increase the surface area, or you could increase the pressure in a gas system. Imagine a low pressure gas system where the particles don't really encounter each other much or with much energy. Also, you can increase the concentration by having you can increase the number of collisions by having a greater concentration, and you can add a catalyst, which lowers down the activation energy by doing one of several or many of several things. There's a whole lesson on catalysis coming up soon. Another thing you can do is stir or mix. This helps to disperse the daughter products and provide more opportunities for collisions. So what about reaction mechanism then? What is that? Except a sequence of effective collisions which together make up the whole reaction. Why do we need a mechanism? Let's look at propanol. If you look at the combustion of propanol and balance the reaction, think, wait a second. Our reaction requires a successful collision, which is rare, between even just 2 particles. How could we possibly happen between the 7 particles that are shown here? Well, the answer is it's very unlikely. Basically impossible for all the particles to meet at the same place and time with sufficient energy and geometry and form all those new bonds at once. And have a look at the next 2 videos in this playlist for more on the topic and our next lesson in Chemistry 12, Lesson 4, Enthalpy diagrams.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe!
Most of these collisions that these guys have, if they actually meet, not making the reaction. But if you get favorable geometry and enough energy and being at the right time and the right place, the right time and the right place is sufficient,